Hello, my beloved students. This is Miss Riwan Hussein from the Science Staff Middle Department EGC. Hope you are doing well. For today, we are going to cover Lesson 3 in Unit 1 for Middle 2 students. This lesson is under the title of The Main Groups in the Modern Periodic Table. As we've studied in the previous lessons, that the modern periodic table is the latest table that arranged the elements. So, in this lesson, we are going to study the main groups in the modern periodic table, which are Group 1A or Group 1 and Group 7A or Group 17. Then we are going to end by some elements and their uses depending on their properties. Let's start in this session with Group 1 or Group 1A in the modern periodic table. We will start by the elements of Group 1A in the modern periodic table. Moving to the position of Group 1A in the modern periodic table, the name of Group 1A, and finishing off with the properties of Group 1A. Let me start with the elements of Group 1 or Group 1A in the modern periodic table. As you can see in the picture, Group 1A includes lithium Li3, sodium Na11, potassium K19, rubidium Rb37, cesium CS55, and francium Fr87. Coming to the position of Group 1 or Group 1A in the modern periodic table. As you can see in the picture, Group 1A lies in the left side of the modern periodic table in S block. Moving to the name of Group 1 or Group 1A in the modern periodic table. As you can see that elements of Group 1A are lithium 3, sodium 11, potassium 19, rubidium 37, cesium 55, and francium 87. If we make electronic configuration for these elements, we will find that lithium 3 is 2, 1. Sodium 11 is 2, 8, 1. Potassium 19 is 2, 8, 8, 1. And as we've studied in lesson 1, that all elements in the same group have the same number of electrons in the outermost energy level. So, all the elements of Group 1A have 1 electron in the outermost energy level. Therefore, elements of Group 1A are considered as metals. As we've studied in the previous lesson, that the reaction of metals with water depends on the position of metal in the chemical activity series, forming metal hydroxide and hydrogen gas. So, let's see a reaction of one of these metals with water. Put a piece of sodium in a beaker containing water and observe what happens. Sodium reacts strongly with water and a gas evolves. Now, Let's visualize this scenario. So imagine we zoom into this beaker a million times. So how is it going to look? It probably looks something like this. Water molecule has 2 hydrogen atoms and 1 oxygen atom. When we add sodium metal to water, sodium atom replaces the hydrogen atom of water, forming sodium hydroxide, and hydrogen gas evolves. So, sodium plus water gives sodium hydroxide and hydrogen gas. If we add a few drops of litmus solution into the beaker, it turns blue, and this indicates the formation of alkaline solution, which is sodium hydroxide. So, elements of group 1 or group 1A are called alkali metals. To test for hydrogen gas, place a lead splint at the mouth of the reaction vessel. You should hear a pop sound. Now, instead of writing the reaction in form of word equation, let's write a simple equation using the chemical symbols of each molecule involved. So, sodium is Na, water is H2O, going to form sodium hydroxide, which is written using the chemical formula as we've studied last year. To write the chemical formula of any compound, first we write the symbol of each element in the compound. So, sodium is Na, hydroxide is OH. Then we write the valency of each element in the compound. So, the valency of sodium is 1. The valency of hydroxide is 1. After that, we exchange the numbers of valency between the two elements. So, sodium takes 1, which we don't write, and hydroxide takes 1, which also we don't write. So, the chemical formula of sodium hydroxide is written as NaOH. Getting back to our equation, sodium hydroxide is NaOH and hydrogen gas is H2. Notice that we've written hydrogen gas as H2 rather than H, and that is because hydrogen exists as a molecule made up of 2 atoms. But our equation is not quite right just yet because we haven't balanced it. In order to be balanced, chemical equation needed the same total number of each type of atom on both sides of the arrow. In our example, we can see that on the left-hand side of the arrow, there is 1 sodium atom, 2 hydrogen atoms, and 1 oxygen atom. While on the right-hand side of the arrow, there is 1 sodium atom, 1 oxygen atom, and 3 hydrogen atoms. So, our equation is not balanced. Somehow, we need to increase the number of hydrogen atoms on the left-hand side of the arrow. As we studied last year, that balancing equation is a process of trials and errors where you keep on changing the numbers until you get the answer. So, to increase the number of hydrogen atoms on the left-hand side of the arrow, we would have to put 2 in front of water molecule, meaning we now have 4 hydrogen atoms and 2 oxygen atoms. This leaves us needing one more oxygen atom and one more hydrogen atom on the right hand side of the arrow. So, to fix this, we put 2 in front of the sodium hydroxide, giving us 2 sodium atoms, 2 oxygen atoms, and 2 hydrogen atoms. Then, if we count all of the atoms again, we can see that we need one more sodium atom on the left hand side of the arrow. And we can fix this by adding 2 in front of sodium atom, giving us 2 sodium atoms. So let's check again. We have got on each side of the arrow 2 sodium atoms, 4 hydrogen atoms, and 2 oxygen atoms. So this is exactly balanced, as we have the same number of each type of atom on both sides of the arrow, and so we are done. So the equation is 2Na plus 2H2O gives 2NaOH plus H2. So, elements of group 1 or group 1A are called alkali metals, as they react with water forming alkaline solution and hydrogen gas evolves, which burns with pop sound. Now, let's move on to the properties of alkali metals. As we studied in the previous lessons, that elements lie in the same group in the modern periodic table have similar properties, and this is because they have the same number of electrons in the outermost energy level. Also, we've just said that alkali metals include lithium 3, sodium 11, potassium 19, rubidium 37, cesium 55, and francium 87. If we make electronic configuration for these elements, we will find that lithium 3 is 2, 1, sodium 11 is 2, 8, 1. Potassium 19 is 2, 8, 8, 1. So, they have one electron in the outermost energy level. Therefore, alkali metals are monovalent elements because they have one electron in their outermost energy levels. As you can see in the following diagram, these elements, in order to react and be stable, all they need to do is to lose this one electron and change into positive ion. And because they lose one negative charge, they change into positive ions which carry one positive charge. Therefore, alkali metals tend to lose their valence electron, forming positive ions that carry one positive charge. As we've just said that alkali metals lose easily the valence electron and change into positive ions, so they are active elements. Therefore, alkali metals are active elements, so they are kept under kerosene or paraffin oil in order to prevent the reaction with moist air. Also, we've just said that alkali metals have one electron in their outermost energy levels. We know that electron has negative charge, whereas the nucleus has positive charge. Therefore, there is a strong attraction between the nucleus and the electrons. And as we've studied in the previous lesson, that as we go down the group, the atomic size increases due to the increase of number of energy levels occupied by the electrons. So, the distance between the nucleus and the electron in the outermost energy level increases. So, the electron in the outermost energy level will be less attracted to the nucleus, therefore more easily to be lost. So, we can conclude that moving down the group, the elements become more active. Let me prove this point to you with some experiments, and you carefully take a look. Which alkali metal is stronger when reacting with water? Let me start with lithium. It reacts with water, giving hydrogen gas. Now for sodium. The same thing happens, although the reaction is more active than that of lithium. Now for potassium. You've seen that the reaction is more active than that of sodium. The next element is rubidium, and this time we put a safety screen between us and the reaction. You've seen that the reaction is more active than that of potassium. Finally, let's try cesium. You can see that the reactions become more terrified as we go down the group. So, the chemical activity of alkali metals increases by increasing the atomic number due to the increase of atomic size. As we've studied before, that the elements of group 1A have one electron in the outermost energy level, so they are considered as metals. And we've studied last year that metals are good conductors of heat and electricity. So, alkali metals are good conductors of heat and electricity. Finally, alkali metals have low densities when compared to other metals in the periodic table. But when we put alkali metals in water, some of them float on the water surface, while others sink in the water. So, most of alkali metals have low density, where lithium, sodium, and potassium float on the water surface, as they have less density than that of water. Rubidium and cesium sink in the water, as they have higher density than that of water. And here comes your turn to evaluate yourself. You can make this more interactive than just watching the video by clicking on the following link on the post or by scanning this QR code, and you'll find a variety of questions on this lesson. So, please do post your answers to the questions or if you have any doubts in the comments, and I promise to reply to all your comments promptly. Thank you, my beloved students. Hope this part of the lesson is crystal clear to you now. See you soon in the rest part of the lesson. Wishing you best of luck. Keep yourself safe. This was Miss Riwan Hussein from the Science Staff Middle Department EGC. Goodbye.